Hello, this is Scholar Strife doing some math, and today in Algebra 2 we'll be looking at inverse and joint variation. So in Chapter 2, Section 5, we explored direct variation. Direct variation is modeled by the equation y equals ax, and we say that y varies directly with x. The non-zero constant a is called the constant of variation. Constant of variation. Notice direct variation is a linear equation such that the y-intercept is 0. So where it crosses the y-axis is at 0, 0. Graph the examples of direct variation and determine the constant of variation. So it looks like y equals ax. So this is in the form y equals ax. So a in this case is negative 1/2. And if we draw it, we start at 0, 0. Oops. And let's see if I can zoom in on this. I cannot, I guess. Okay. Well, anyways, 0, 0 is right there. And then, hopefully you remember how to graph a line. Down 1, right 2. Down 1, right 2. And up, left 2. Up 1, left 2. And then go ahead and draw your line. So this one I have to change it so it's in y equals ax form. So I'm just going to move x over by multiplying both sides by x. So I'll get y equals 5x. So my a value is 5. So back at 0, 0 again. Up 5 over 1, up 5 over 1. Down 5, left 1, down 5, left 1. There are many real-world applications that model direct variation. For instance, we can say that distance varies directly with time at a constant rate, giving us the formula d equals rt, where d varies directly with t, and the constant variation is r. We could list a simpler example, such as the more you study, the better grades you get. Since both studying grades are increasing, this models a direct variation. Now, in Chapter 8, Section 1, we are looking at inverse variation. We say that two variables x and y show inverse variation if they can be modeled by the equation y equals a divided by x, where a cannot be equal to 0. The non-zero constant a is still called the constant of variation. Constant of variation. We say that y varies inversely with x because as one variable increases, the other decreases. The equation y equals a over x can be solved for a for an equivalent statement. Solve for a now. If we wanted to solve for a, we'd just multiply both sides by x and get x times y equals a. The graph of an inverse variation equation is the shape of a rational equation where the variable is in the denominator. So this left picture here. Let's try to graph one. So basically what's going on here is there is a vertical asymptote going on. Because if you compare it to the other graph, you see how it's approaching the y-axis but never touching. And then we're just going to make a table. Let's have 2 to the left of 0 and 2 to the right. So -2, -1. And then, I guess over here, since I don't have any space, 1 and 2. So if I plug -2 in the equation, I get -1. Plug in -1 in the equation, I get -2. If I plug in 1 in the equation, I get 2. Plug in 2, I get 1. So what this is going to look like is 1, 2, 2, 1, -1 is -2, like that. So this is the general shape. So notice how they're also approaching the x-axis, but never touching, because there's also a horizontal asymptote there, but we'll go over those later. An example of an inverse variation is that the length L of a rectangle varies inversely with its width, given a constant area. So this gives us the equation length equals area over width. A simpler example is the more you slack off, the worse grade you will get. We're also looking at a joint variation, which extends direct variation to get the following. Z varies jointly with x and y, given that z equals a times x times y. This could be extended to even more quantities, such as p equals AQRS. Basically, it's saying there's like different variables affecting an outcome. Classify each equation as direct variation, inverse variation, joint variation, or none. So xy equals 7. If I move x over to the other side, or if we remembered from before, this is known as an inverse variation. Because if I do divide by x to both sides, I'll get y equals 7 over x, which looks like y equals a over x. So this is a inverse variation. The second one is a simple y equals mx plus b. It's just a line. There is no direct variation, inverse variation, or joint. So this is considered none. This one, if I multiply both sides by 4, I get y equals 4x, which looks like y equals ax. So this is a direct variation. And then lastly, this one is a joint variation. Y varies directly with w and x. Alright, part B. Writing an inverse variation equation or joint variation equation. So the variables x and y vary inversely, and y equals 7 when x equals 4. Write an equation, then find y when x equals -2. So we're looking at the words varies inversely. Okay. So inversely looks like this, y equals a over x. So they tell us y equals 7 when x equals 4, and that'll allow us to find a. So y, which is 7, equals a over 4. Multiply both sides by 4, and we'll get 28 for a. Now we can rewrite the equation. Y equals 28 over x. So that's my equation. That's the first part of it. And now they want us to find y when x equals -2. So y equals 28 over -2. So y is 14, or -14. Okay. Part 2, x and y varies inversely. So same thing again. So y equals a over x. And they give you an x and y to work with, but just in a different way. They tell you that the point 1/2 12 lies on the curve. So x is 1/2, y is 12. So this is going to be 12 equals a over 1/2. Okay. So if I multiply both sides by 1/2, I will get 6 equals a. So my equation is y equals 6 over x. Now we need to plug in 2 for x. So y equals 6 over 2. So y equals 3. The variable z varies jointly. So the key words here, varies jointly. So z equals a x, y. And then they give us z, x, and y, so we need to find a. So negative 75 equals a times 3 times negative 5. So I have negative 75 equals negative 15a. Divide by negative 15, and we'll get a equals 5. And so here's my equation. Z equals 5xy. And now we need to find z when x is 2 and y is 6. So z equals 5 times 2 times 6. 12 times 5 is 60, or 10 times 6 is 60, however way you multiply that out. Alright. So we're going to actually skip this example. So, example D. The table below compares the current with the resistance for several electrical circuits. Determine if the table shows inverse variation. So if they show inverse variation, that means if we multiplied them together. So inverse variation means there is a constant value that makes it look like this. So if I multiply I and R together, they should get around or the exact same number. So let's make a table. So this is going to be I times R. So for example, 7.4 times 1200, 8.9 times 1000, 12.1 times 750, and 17.9 times 500. So if I multiply all these out, I'll get an A value of 8,880. This one is going to be 8,900. This one's going to be 9,075. 8,950. Now these don't necessarily match, so you could say they don't show inverse variation, but they're kind of quite close together. So you could say that the A value in this case is 8,900. So you could say I equals 8,900 over R. You could do it that way, just because they're so close. But in the problems that you'll do, they will be more exact. These would all come up 8,900. Let's move on to the part E. So write an equation for each relationship. So y varies inversely. Y varies inversely, which means y equals a over x. And that's it. Oh wait, with the square of x. That's why make sure you pay very close attention. The square of x is x squared. Okay, so y equals a over x squared. Number 2, x varies jointly with t and r. So x equals a t r, and inversely with s. So that means we just put it in the denominator. So if it's either directly or jointly, it goes up top with a. If it's inversely, it goes in the bottom. So p varies jointly with q, or, well, don't forget to put a, q, r, s, and inversely with the cube of t. And then lastly, x varies directly with y and inversely with z. Hopefully this helped you out. Have a good day.